Geometric proofs. In this section we're going to see how vectors can be used as a tool for proving geometric results. There's a couple of definitions that we need. Collinear points, when there's three or more points, are collinear if they lie on a single straight line. So that's an example of collinear. And concurrent lines, three or more lines are concurrent if they all pass through a single point. There we go. Some of the properties of vectors that might be able to help us. For k is an element of rules positive, the vector ka is in the same direction as a and has magnitude k, magnitude of a, and the vector minus ka is in the opposite direction to a and has magnitude k, magnitude of a. Vectors a, b are parallel, then b equals ka for some. K is an element of rules, not including 0. Conversely, if a and b are non-zero vectors, such that b equals ka for some k not 0, then a and b are parallel. If a and b are parallel with at least one point in common, then a and b lie in the same straight line. An example, if ab equals kbc for some values of k, of course not 0, then a and b are collinear. Two non-zero vectors a and b are perpendicular if and only if a times b equals 0. And of course a times a is the same as the magnitude of a, all squared. Example 15. 3 points P, Q, and R have position vectors P, Q, and K, 2P plus Q respectively relative to a fixed origin 0. The points O, P, and Q are not collinear. Find the value of K if QR is parallel to P. Okay, so QR will equal QO plus OR. QO is just OQ, but negative, so that will be negative Q. OR we've already got, so plus K, 2P plus Q. And I can rearrange this by putting the Q's together, so I'll get 2KP plus Q, K minus 1. There we go. But if QR is parallel to P, then there is some values. We'll call these values this. It doesn't really matter what we call them. Of course, it cannot be 0, such that what we just got, 2KP plus Q, K minus 1, has to equal some of this. Okay, has to be. If it's parallel to P, that's why I've got the P there. Implies, well, the only one that's got the P here is the 2K. So it implies that 2K has to equal P. No, sorry, has to equal that, and K minus 1 has to equal 0. Therefore, K equals 1. Part B, PR is parallel to Q. Again, PR has to go from P to O plus the O to the R. P to O is negative P. O to R is K to P plus Q. And of course, rearranging this one, I get 2K minus 1P plus KQ. Of course, if PR is parallel to Q, then there is some, we'll call this letter M, which is an element of rules excluding 0, such that what we just got, 2K minus 1P plus KQ, will equal M, this time with the Q, because it's parallel to Q. Implies that 2 k minus 1 equals 0, and k equals m. That's not going to help us, but here 2k will equal 1, k will equal a half. Now, we should note that since the points O, P, and Q are not collinear, the vectors P and Q are not parallel. So just to note that. Part C, P, Q, and R are collinear. Now, if they're collinear, then there has to exist something, n, which is an element of reals excluding 0, such that n, P, Q will equal Q, R. Okay, because if they lie in the same line, then P, Q has to be Q to R. Now, sorry about that phone. I'll continue with it. So PQ, we will be, if we work that out, we'll get negative P plus Q. So therefore I get N, negative P plus Q, and QR we've already worked out, will be 2KP plus K minus 1Q. And this implies, putting things together, that minus N, because there's our P, putting the P's together, so I've got the minus N, will equal to K, and putting the Q's together, it will be N equals K minus 1. But I know that minus N is equal to 2K, so I'm going to substitute that in there. So I'll have minus 2K, or equal K minus 1, because if minus N is 2K, then N is negative 2K, and therefore I have 3K minus 1 equals 0, 3K equals 1, K equals a third.